Okay, any questions about the exam or the midterm review before we get started today? Okay, I made the exam 3 hours now, so hope that's okay. Same amount of questions, so I don't think you should be too rushed on it now. Still open everything. Okay, so let's see. Today we're going to talk about feature selection and engineering, which will actually be nice because feature selection is kind of a good review for the exam because a lot of the feature selection methods are repurposing of methods that we've already learned about. So I think it's a good method to cover. It's also important for homework 4. So feature selection, if we remember from before, is where we remove features, so inputs to the model, remove features which are not helpful, for prediction. And hopefully you remember why feature selection is important. If we have too many axes, too many inputs, we could overfit the model to be overly complex. Yes.
So they were talking about in ICS 637 today, and what Dr. Sadowski said is that that's how it works in theory, but that's not how it works in practice.
How what works?
That having too many features doesn't actually hurt in practice.
It can. So we saw examples where it can definitely hurt depending on your model, and perhaps it, for a neural network, things could be a little bit different than the models we've talked about.
Maybe that's because the neural network. I don't know. I'm just saying.
And the nice thing about neural networks, which we'll get to, is everything we're covering today, feature selection and feature engineering, is kind of automatically done by neural networks for you. So you don't even have to do it when you have a neural network, but we'll get to that later in this class. But if you're using a traditional machine learning method, which is all that we've covered so far, you'll have to, sometimes you can have too many features, and sometimes you might want to engineer your features to be useful for prediction. And we saw exactly why it could overfit. If you have a variable that doesn't have anything to do with your outcome variable, so, for example, just to review, x1, x2, and let's say we're doing classification, and let's say it's only x1 that makes a difference, and we have this type of data, then the model might learn a decision boundary that's like that, when really it should just be learning a line on x1 that separates the data. So if you get rid of x2, it's not even an issue because x2 is kind of adding noise. So that's why we do feature selection, and there's many different ways to do feature selection, and there's not necessarily one right way or wrong way, but there's trade-offs between them. So we'll cover a few of them. And the first few are just repurposing methods that we've already learned. So that's why this will be good for midterm review. So the first is L1 regularization, and we talked about how this can be used for feature selection before. If you recall, L1 regularization, just in one phrase, is penalizing weights by adding a lambda term, just a hyperparameter, times the sum of the model weights, the absolute value of the model weights, to the loss function. and we drew pictorially why that leads to L1 regularization. But just to quickly draw it again, third time's a charm, or is this fourth time? Anyways, we're jointly trying to optimize the sum of the model weights, and if we draw all the model weights that lead to a certain penalization, we see that as we increase lambda, where we have greater diamonds, because lambda is telling us how much we're trying to optimize, how much we're penalizing the weights, and we might have our place with our minimum mean squared error over here. And so as you go away from that mean square error, and as you expand out the diamond of your loss function term with the increased lambda, the place where these two meet tend to be at these corners of the diamond, and that's where you set one parameter to 0. So in this case, theta 0 is set to 1, but theta 1 is set to 0. So it just so happens that when you have many features, it tends to intersect the multi-dimensional version of a diamond in higher space. So we talked about this already, but so L1 regularization, therefore, is just one way of automatically removing weights. Method 2 is decision trees. So even if you're not using a decision tree as your final classifier, decision trees automatically perform feature selection for us. So decision trees.
L regularization is a type of feature selection.
Yeah. Forms feature selection for us, where the most important feature is at the root of the tree, and as you go down the tree, you have progressively less important features. Keep going, ... And you can use the top n nodes of the tree as the top n features. And what's nice about decision trees is that it's conditioned on selecting another feature. So feature 2, you might, let's say there's a feature 4 that's not on here, where given that you've selected feature 1, even though feature 4 is highly predictive of the outcome, after you've selected feature 1 and selected and seen the value of feature 1, feature 4 is no longer so important because it's highly correlated with feature 1. Decision trees automatically handle that for you, because after you split, you then only consider given that you've already done the split. So it gets that conditional setting nicely. The third method for feature selection is linear and logistic regression. We'll talk about how. So when you're fitting a linear or logistic regression model, let me just finish this and I'll take the question. We recall that we learn, in the case of logistic regression, sigmoid of mx plus b, and let's say we have learned these specific weights after running gradient descent. What we know from looking at the weights is that by looking at the learned weights, we can say that x1, that input contributes strongly towards, let's make this a prediction of cancer. So X1 contributes strongly towards cancer because it's a positive coefficient, and it's a large positive coefficient, so it's making the output go more towards 1. X3 contributes strongly towards no cancer for the same reason, except it's a negative coefficient. So the larger that X3 is, the more the output tends towards 0. And the absolute value of the coefficient is 15. So it has a large contribution towards 0. And this one, X2, technically does contribute towards no cancer, but it's a really small coefficient, so we could remove it because it doesn't have a huge effect on the model. So X2 technically contributes to no cancer, but the coefficient is small, so remove this feature. So that's something people commonly do. They fit a model, they look at the coefficients. If the coefficients are small, that feature isn't contributing strongly towards the outcome. Method 4, and this will be the last of the review. Oh, sorry, question?
This method 1, 2, 3, I guess now 4 are these ranked?
No, there's no ranking to any of this. I'm just listing.
Okay.
And, you know, technically method 3 would probably fit better after method 1 since they're both linear logistic regression. But this is just the order that I thought of them in. Yeah, so no ordering, or the order doesn't have any meaning. Method 4 is mutual information, which actually turns out to be information gain from decision trees. So we can rank features by their information gain. And recall that information gain of any particular input x on the outcome variable y would be the entropy or the uncertainty of y minus the entropy of y given x, where recall that the intuitive interpretation of this is the uncertainty of y. This is the uncertainty of y if you know x. And therefore, when you subtract the two, it's how does knowing x affect y? So if you do this for every input feature, you can see which one gives you the highest information gain and prioritize that feature or the features with the highest information gain. Method 5 is statistical, just looking at statistical correlation. Statistical correlation. How many people have taken a stats class where you do like R² and correlation coefficients? Okay, so basically you do that, and we won't cover the details here. There's many different types of, in statistics class, you learn all these different types of statistical tests, and some of them deal with continuous variables and continuous outcomes. Some deal with categorical variables, categorical outcomes, chi-square. Don't worry about that for this class. Just know that there's a statistical test for the types of variables that you're dealing with, and we deal with lots of variables. We deal with continuous variables. We deal with categorical variables. And you just look up which test do I use when my variables look like this, and then you run that test, and then you look at the test statistic or the correlation coefficient and sort according to that. So I'm just going to draw it for a Pearson correlation coefficient, which is where you have two continuous variables, but you don't have to know that for this class. Sort features by the correlation coefficient, although you definitely should know this if you're going to be a data scientist or a regular scientist. Sort features by correlation coefficient between feature and outcome variable, and recall that. Actually, let me add by absolute value of the correlation coefficient. You'll see why when we draw it out. This would imply a really strong negative correlation. This would mean a really strong positive correlation. And this is what you learn in stats class. X, Y. This would be no correlation. Just two more. This would be correlation between 0 and 1, and this would be correlation between -1 and 0. So if you take the absolute value, it tells you which ones are of the correlation coefficient. It tells you which outcome variables are most correlated with the outcome variable, which input variables are most correlated with the output variable, which is good, but let's reflect on what we have so far. So statistical correlation just looks at each independent variable, independent of all the other input variables. Same with mutual information. You're looking at what's the information gain if you know that variable. But some of these other ones, like decision trees, notably, look at the input variables with respect to each other. So given that you know the value of one input variable, you might not need to know another input variable, even if those two input variables both have equally strong absolute values of their correlation coefficient. So so decision trees are nice for that reason. One other method that's nice for that reason, and which is the last feature selection method we'll talk about, is called recursive feature elimination, often abbreviated as RFE. And the key insights for this one are, again, that one, the features often have complex nonlinear interactions, have complex interactions / dependencies. Actually, I'm not going to do a list. That's a good enough key insight. So, for example, you might have score, like 2 features maybe. Actually, can anyone think of 2 input features that might be highly correlated for any type of AI model?
Height and weight.
Mm-hmm. Yeah, and for height and weight, you might, going off that, you might have something like if your BMI is between 18 and 25, that's associated with being healthy, according to the numbers, with being healthy. But it's a little bit more complicated than that, right? Because if your percent body fat is less than 2%, then maybe a BMI that's between 24 and 32 is associated with healthy. I'm just making these numbers up, but you see what I mean. If percent body fat is less than 2%. So, or another example could be score on the midterm and score on the final. Perhaps if you're predicting some outcome about a student, like whether they get hired or something at some company, you might not need to know both the score on their midterm and the score on their final, because if you know the score on their midterm, that's highly correlated with the score on their final, and so adding the score on their final is not going to give your model too much additional information. Just things like that you can think of in the real world. So what are the steps to RFE? Steps to RFE. And this is sort of a meta algorithm, but we do a while loop. So while the number of features is greater than the desired number of features, we train a model, could be any model, using, or whichever type of model we want to use, using the current set of features. We then rank the features using any features ranking method, like the ones we talked about above. So, e.g., the ones above. And then we remove the least important feature. And then you loop again, you train the model with the n-1 features, you rank them using some method, you remove the least important feature, and you iterate and iterate. Yes, question?
Isn't this a little bit like bootstrapping?
So the question is this like bootstrapping? Not quite, because bootstrapping is where you generate many independent data sets, where this is each iteration is highly dependent in this one. Maybe it's like AdaBoost.
Do I mean Jackknife, the one that you keep might remove certain things?
I think maybe boosting. It's somewhat similar to boosting. Okay, so I think that's all I have to say on feature selection. Any questions on feature selection as a whole? Hopefully it's a nice review for the midterm and a new concept at the same time, which is always good. And so feature selection and feature engineering, we're now going to move to feature engineering, are going to be the key to the coding portion of homework 4, where it's actually so homework 4 has really similar setup to homework 3 and 1, where there's some written questions and then a coding question. But interestingly, the coding question is really similar to homework 2, but it's a different data set. It's an image-based data set. And this time, instead of choosing the best model, the model's fixed, and what you do is choose the best feature representation. So the input data is inputted, and you have to return a new version of the input data that's going to make the model perform much better. And we'll do another contest and all of that. So it should be pretty fun. I have some screenshots of the homework. So, same thing, really similar setup to before, but now we're using a face recognition data set. So more real world. As you get more advanced, we can use more real world data sets, which is exciting. And right now, we have this transform input data function. That's the only function you're allowed to change. That takes as input the X data, and you return the modified version of the X data, where the baseline implementation is super basic and not going to give you the performance you need. And then logistic regression is going to be used to train the model no matter what. So you can keep that in mind as you're engineering your features or selecting your features, or both, that you're using a linear classifier. So that might be useful to know. Maybe it's not useful to know, but it's something you should know. Okay, so this is very timely, so that over spring break you can think about how you want to tackle that question, which should be pretty fun. Okay, so now let's talk about feature engineering, where recall there's many ways to transform our data. We talked about feature selection. We're now going to talk about feature engineering, and then dimensionality reduction we'll talk about after the break, because next class we're talking about, so announcement, by the way, Tuesday, their final or midterm will be done. And if you're only show up on Tuesday if you're in 435, and only show up on Thursday if you're in 635, because we'll go over class-specific final project requirements, because it's a little different. I mean, it's more or less similar, but there's slightly different requirements since grad students have different learning goals in general. Okay.
Question.
Yeah.
If you're like a grad student 435 and undergrad 635, you go to the one that you're in, not the one that your student does.
I mean, yeah, I don't know. That's an interesting corner case. Mostly it's for undergrads in 435 and grad students in 635, right?
I'm an exception to that.
Okay. Let me think about that. I'll send a announcement about that. I need to think about that case. Okay, so let's talk about some common feature representations for natural language processing. That's a very common AI task, and also for computer vision. So that's the outline for the rest of today. And starting with NLP, so common feature representations for natural language processing. The first one you've already seen in the coding notebook from before, bag of words. Just to go over it a little bit more formally though, because it is so commonly used. You create a vector with length being equal to the number of words to consider. You use one vector position per word, and the value in each position is the number of occurrences of the word. So for example, if we had a sentence that was like, great food, great music, and great vibes, that might translate into having a position of great with 3 in it. There might be other words that didn't appear in the sentence that we're representing, but which are nevertheless ones that we think are important. And etc. And we generate a vector like so. And really the only other thing to note about bag of words is that the vector is of length n, where n is a hyperparameter and only the top n words, but only, whoa. Oh. Sorry about that. Where n is a hyperparameter and only the top n occurring words, frequently occurring words, top n frequently occurring words are included in the vector. So that's often called a dictionary. And I think in the Python notebook from that coding class, we called it a dictionary. So that's bag of words, relatively simple, but it leads into the second common representation in NLP, which is actually much more common, which is also used in search engines and information retrieval. It's called, I don't know what's wrong with my, sorry, it's not letting me scroll. Okay, there we go. Apologies, lots of technical difficulties today.
Scroll it down.
Sure. Term frequency, inverse document frequency, oh my gosh, sorry, TF-IDF. So whenever you see TF-IDF, it's term frequency, inverse document frequency. And the key idea is that we associate each word in the document with a number, just like in bag of words, with a number representing how relevant that word is to the document. And TF-IDF has a relatively simple equation. It's equal to the TF times the IDF. I don't know why this keeps rolling up. Times the ID, where TF stands for term frequency, and IDF stands for inverse document frequency. So let's break apart each of these terms of the equation. So term frequency,
No, wait,
which we'll denote as TF of T and D is the relative frequency of term T within document D. Relative frequency of term, which is just another term for word, of term T in document D. And so you could write that in as the frequency of term T in document D, but it's relative, so divided by the sum of every term. I don't know. Sorry.
I want to like restart it.
That's
Help, because this will just show up in the recording.
that's of every other word in the document frequency. The frequency of the word in the document divided by the sum of all of the frequencies of every word in that document. So that's term frequency. The other term is inverse document frequency. Sorry? T prime, which is an element of the set D, of the f of T prime and D.
Can you say that again? Oh.
Element of. Element of. And the T prime is every other term. So just over the sum of every other, not every other, all the words in the document frequency summed up. Inverse document frequency, which we will denote as IDF of T and capital D, is a measure of how much information the word provides within all the documents. So measure of how much info the word provides within all documents, which is denoted as D. Okay, let me try restarting this notes app, see if that helps. Okay. which is denoted as of the number of documents, which can be represented mathematically as the cardinality of capital D, where D is the set of all documents, divided by the number of documents word T appears. And side note, we can apply smoothing like we do in naive Bayes, well, another nice thing to review for the midterm, so that if there are no documents where word T appears, you don't divide by 0. So same, you can do that type of smoothing just like you do in homework 3. So the reason we use these is that notice that the inverse document frequency is 0 when the word appears in every document and the IDF, because we're taking the log, increases logarithmically as the number of documents, number of docs where word T appears in increases. So if we draw a little graph where the x-axis is the number of docs that T is in, the x-axis, and the y-axis is the inverse document frequency. It increases logarithmically, and therefore as if we have that same axis, x-axis, so number of the docs where that T is in, and the x-axis and the TF IDF, as the y-axis kind of has the reverse curve. At least given the same frequency within the document. And then once we have that representation, which people kind of played around with different ways to represent it, and they've just kind of found empirically that TF-IDF tended to perform well, which is a common theme in machine learning, then what we can do is, so then we can create a bag of words vector, or maybe a bag of words style vector, using the TF-IDF representation of each word. Using the TF-IDF representation of each word. So as an example, let's say that we have 2 documents. We have this document, and each document has text, and it has a number of words. So we'll just have 2 document examples. Document A and document B, where document A has the text Jupiter is the largest planet, and document B has the text Mars is the 4th planet from the sun. Those are facts. Then we can calculate, might be overkill to do this example because I think it's clear, but just so you see it, we can get the term frequency for document A for each word, the term frequency for B for each word, and then the corresponding inverse document frequency. So we have Jupiter is the largest planet. Mars appears in the other document. Fourth planet also already appears. From doesn't appear. The already appears. And then sun. So these are the unique words. And so the term frequency for the documents in A are all 1/5. They all just appear once, and 0 for the other words. And for document B, term frequency is 1/8, 2/8, 0, 1/8, 1/8. All these other words just appear one time in the document. So in the inverse document frequency, we'll just maybe calculate it for the first one. So the log of 2/1, which happens to be 0.69. And so if we do that same type of calculation for all the other words, we happen to get this representation. And so the TF-IDF do it for word A, because I mean document A. So once we multiply the two terms, we get something like that. And so our document A representation that we feed as input to our machine learning model would be, well, we need a, wait 1 second. We need one position for each of the words. And we put in the term frequency for each of the words, and it's 0 for all the other words. So we would put that vector representation of our sentence into a machine learning model if we wanted to predict something about document A, and we do that for all the other documents. And really intuitively, documents with similar relevant words will have similar feature vectors. So that's really the only reason why this works well.
Wait, can you scroll up a little bit? Just see.
Don't worry, the specifics really don't matter.
I'm just trying to copy it down so I can use this as an example later on.
Okay. Documents with similar relevant words will have similar feature vectors, and that's a good property. I'll scroll up a little. That's a good property to have if you're representing your data. If you want similar data to have similar numerical representations. And so TF-IDF has done pretty well. And actually, one way that search engines were implemented, now they're much more advanced, but you can imagine implementing a search engine where you take the TF-IDF vector representation of every web page, and you then do a k-nearest neighbors type of thing where you have your query, and then you get similar, I mean, it doesn't, with some modifications, but that type of thing where you're looking for similar documents to a certain. So you're not searching for a text, but you're searching for similar web pages to input web page. This type of thing could work, and this was what was done a long time ago. But now it's like this plus many other things all together working in one giant system, which includes TF-IDF as part of it, but many other things, components as well, to have state-of-the-art search engine. Okay, so there's many other and actually more popular representations in NLP, but they're not engineered. These are automatically learned using AI, and we will get to those later. So we're not done talking about NLP. We're just done talking about the representations in NLP which are engineered. That is where there's a deterministic output. There's no prediction of what the representation should be. But now the state-of-the-art methods involve putting in the text into an AI model, which outputs the best representation of the word. And we'll get to that later. Kind of history of AI and ML, we started with these engineered features, and then we got to these automatically learned features, which we'll get to in this class. So this class is kind of going in how the history of AI development went. Do y'all know about ChatGPT? How would y'all feel if we ended with how ChatGPT works, like as the last class? Would that be interesting? Okay, so we're gonna slowly build up to there. So just know when we get there that we started with TF-IDF, but it'll be much more advanced by then. So just final note, that bag of words is just the TF part of TF-IDF. So bag of words is the TF part although bag of words is not normalized, but basically the same thing. Okay, so now let's talk about common feature representations for computer vision. So common feature representations for vision. And this is, in a computer vision class, discussed extensively. So we're not going to go into all the detail that a computer vision class goes into. We'll just cover some of the basics and just a small subset of the feature representations. So one is to just use the original image, because unlike text, images are already a numerical representation. So specifically, let's say we wanted, or not that we want to do anything, the representation of this image, let's say we're having an image of a purple T, the letter T, and it's a highly pixelated 3x3 image, but because it's just a 3 pixel by 3 pixel image, but because it's just a T, the pixelation doesn't matter too much. So the way that this image would be represented on a computer basically universally is that you have 3 matrices, RGB, one for each of your color channels. And so you actually have a 3-dimensional input representation, width of the image by height of the image by RGB. The RGB is the 3rd dimension. So we have our red channel. Did we already cover this in class? What? No. No, okay. Green channel. I always talk. Sometimes I forget if I talked about it in class or somewhere else. So the way we do this is the red channel represents, so in computer vision and in general in color theory, you can, if you combine any combinations of intensities of red, green, and blue, you can derive any color. So these are kind of a subspace that allow you to get any color that humans can see, different combinations of an amount of red, amount of blue, amount of green. So if we want a purple T, then using color theory, we'd combine red and blue from like art class. And so the maximum value that computers use to represent the intensity of any given channel is 255. You might have encountered that in image editing programs. So we'd have 255 for the T parts of the image in the red channel, a same thing in the blue channel, because the image purple for the T, and so that's equal combination of red and blue. And the green channel would just have zeros everywhere because it's a purple T, not whatever you get when you combine red, green, and blue at equal intensity, which would be white, by the way. And so black is 0. You could think of it as the absence of light, and so it's represented as 0, whereas 255 is the maximal light. So that's how computers represent white. So basically the number represents how much of that color, how much of that light is represented in the image. So that's one way to do it. You can just use the baseline image because it's already a numerical representation. So you don't even have to convert it to a numerical representation. The problem is that images are super complex, much more complex potentially than text, because they have all these things that they're describing, and often it's really easy to overfit. Imagine you have an image with what's a normal image size, like 512 by 512, that's still a relatively small image. And so 512 times 3 pixels, you have on the order of 1,500 pixels. It's really easy to overfit with all those inputs, where each pixel is a different input to the model. So one engineering approach is to apply what's called an image kernel, which is different than a kernel that we talked about in SVMs. Same word, but different meaning. Apply an image kernel throughout the image, and this is a fancy way of saying this is apply a convolution, which is the same convolution of convolutional neural nets, but we're not talking about convolutional neural nets today, although this is kind of leading up to it. So a kernel in the context of computer vision, which is, again, different than an SVM kernel, is a small matrix. So is a small matrix applied via a sliding window. This will all make sense in a bit. Sliding window, we'll just define it and then we'll draw it out and then do an example. where as you're applying the sliding window, you take the dot product between the original image portion and the kernel portion to
Did that say take dot product?
take the dot product. I don't know if that clarified it. And kernel to get the new pixel value for that position. So we'll do an example, but first let's just see this visually.
Sliding window.
Yeah, we'll go through that. So let's say that this whole box is the original image, and we have a small 3x3 kernel, which is a different matrix. We take the dot product between the kernel and that small portion of the image, and then we slide the kernel over, so now it's from here to here, and we take that dot product, and we keep on sliding it all the way across, and then we bring it down, and we continue taking the dot product through each row of the image. And as we go, as we do this, this is what the convolution is. So you might be wondering, why are we doing that? It seems like overly complicated. What's the purpose of doing that? Well, it turns out that you could engineer these different kernels so that when you do this dot product, it results in a specific transformation of the image. So different, and you'll see this, you'll gain more intuition on this really soon. Today, hopefully, different kernels filter images in different ways. So you could often call a kernel a filter. It's kind of a synonymous term. So for example, you can blur the image. Then there's a certain kernel that blurs it, and we'll see why in a bit. You can define a different type of kernel that will sharpen the image. You can define a different kernel that will detect edges really well, and many other types of filters. So you're probably wondering, okay, how are you blurring the image from doing this? This seems like a really complicated process, and why is this resulting in blurring? So I think the easiest way to see that, and then we'll come back to an example, is actually through this website that I found, which I think does the best job at explaining this more than anything else I can do. So we can choose a different kernel. So let's start with a blur kernel. So it turns out that if we do the process of sliding that kernel, taking the dot product and putting the dot product as the new pixel value in the corresponding image, that this particular kernel has the effect of blurring the image. But why is that? Well, notice that the kernel has relatively low values for all of the, for each position in the kernel. So if we're where this red dot this red 3x3 grid currently is, when we take the dot product, we get the corresponding pixel value in the output image. So if we slide this 3x3 window over by 1, we get that other corresponding pixel. So where it's labeled input image and output image. So notice every time you apply the kernel to a 3x3 portion of the image, take the dot product, what you get out of that is one new pixel value. And so this particular setup of the kernel, if you notice what it's doing is it de-emphasizes differences in adjacent pixel values. So that is that even though we're in the input image where this 3x3 red box is, currently has very different pixel values in that 3x3 grid, by applying this kernel, it's de-emphasizing those differences. And if you imagine doing that as you slide, you're de-emphasizing the stark differences between those kernels by having between those pixels by having a kernel with relatively similar and small values within the kernel. As you slide that through, you're not going to have as drastic differences in the pixels, and therefore that has the effect of blurring the image. Let me show you one more example, and then I'll take some questions. So let's say we want to detect edges or outlines. We have a very different kernel in this case. We can have -1s everywhere with an 8 or a large value, it doesn't really matter what it is, in the center. And this kind of does the opposite. It highlights large differences between pixels and really exacerbates them. And the reason is that whatever pixel value you have in the center has a large positive weight, whereas all the pixels surrounding it have a negative weight. And so that difference is really exacerbated so that when you're over here in the image, it's a relatively darker pixel, and it's emphasized to be darker there. And if you look over here, the center pixel is dark, so the output pixel is dark, but if you slide it over one, the center pixel is lighter and the output pixel is lighter. And again, the reason is because of the way the kernel's set up. So the cool thing, and a lot of this whole field of computer vision and image processing and what you learn in computer vision is how do you engineer these kernels or these filters that are applied to images such that it does what you want to the output image. And you could kind of just reason through it like we did just here. There's no mathematical proof. It's just like, yeah, I could kind of see why this does that. And sometimes there are mathematical proofs, but you could kind of see it intuitively here as to why certain kernels have different effects to images. And when you're in Photoshop and all these image editing programs, this is basically what it does. It applies these filters across the image to get the output image that you want. Yes, question?
I mean, in the case of the blurring, aren't you just doing some kind of averaging? You're basically doing a kind of weighted average of almost all of them, isn't it?
Yeah, great question. So the question was, for the blurring one, couldn't we have just had the exact same average it and just have the exact same values in every position in the kernel? There are other versions of a blur kernel that do exactly that. So there's different types of blurring. This type of blurring is slightly different. There's like Gaussian blurring, which is what this is, where it's kind of normally distributed, whereas you can have uniform blurring or average blurring, as you said, which is imagine having 1/9 as the value.
The math behind it is basically some kind of a weighted average, more or less.
Yeah, for that type of blurring kernel. Yeah, so there's, so a lot of computer vision is coming up with the right kernel to use in a certain situation and applying it across the image. Any questions on that? Okay, a cool thing when we get to neural networks and convolutional neural networks is that we learn, just like with NLP, where, okay, we have bag of words and TF-IDF, but the best ones are automatically learned. Same thing for computer vision. So yeah, you could take all this time to try to figure out the right kernel, but what's actually done today is that the best kernel to use, and really kernels to use, are automatically learned by the model. And we'll learn about those types of models coming up, where, yeah, maybe detecting edges will be very useful for the types of classification we want to do, but maybe it's this complex task that is hard for the human eye to understand, but that that computers can do a really good job of looking at and understanding, even though visually a human is not really seeing these patterns. So more of that to come later. Let's quickly do if we have time, just an example of the kernel calculation. And let me maybe put in the notes to check out that website, which is, where's the website? Setosa.io. Excuse me. /image kernels. Cool website. Okay. And just play around with that, and that'll really help you understand when to use what type of kernel. Okay, so let's say we have our original image, and we'll just make it be one of the color channels for the T image that we saw above, so that 3x3 highly pixelated image with the 255s in the positions for the T and zeros everywhere else. And let's say we're applying this kernel then the first thing we do is take the dot product between this portion of the input image, the top left of the input image, and dot that with the kernel, 0, -1, and that dot product, I won't write this out for all of them just due to time, but just for this first one, 245 times -1, which happens to be 265. So the new image so far is we have the 265 in the top left corner. We don't know the other values, what the other values are, but then we do the same thing for the other positions. So that would be 255. So looking at this top right portion of the image, 255, 255, 255, 0, dot the kernel. We have the bottom left portion of the image, which is this. And finally, we have the bottom right portion of the image, which is, which happens to be 510 for the first one, -255 for the second one, and 490 for the third one. So finally, the result of the convolution, to use the technical term, is this 4 by 4 grid, which will happen to have the properties of whatever the kernel that we have is. But that's basically what a kernel's doing. You slide the kernel across the image, take the dot products, put it into the corresponding position of the new image. Okay, so next week we'll talk about the final project and then spring break. Then we'll go into a lot of fun things in the second half of this course. Good luck on the midterm.